Okay, let's insert here text box. So you had homework 3, and homework 3, it was really like a small exercise of how, of how some important applications of deep learning are implemented. So always you had to do the labeling, and then after the labeling, I was asking to do the labeling of curved objects by carefully drawing borders. Okay, so that was labeling because we wanted to determine the total area with high precision. Okay, and in homework 4, you will actually the directives of how you can implement homework 4, they are already given in the Google Classroom. But what I have not done yet for all of you, I have not shared the labels that all of you have conducted. So then you will calculate the IOU for all labeled images. And regarding this, I will share the labels of everyone in the class. Meanwhile, I can also, what would be project, for some of you have a project of trying to detect objects using UNet, where UNet is a modern architecture, modern misspelled, of course, modern network architecture to detect objects. Now, I'm going to pose like a challenge to detect the objects that you labeled. Okay, it is challenging. It is not. It's not straightforward. Okay, and you might also have a look at how difficult it could be just by implementing, or let's say, just by running some public code which you can find in public domain. So you can check the accuracy you can obtain without doing too much pre-processing or pre-preparation or data augmentation. So I can strongly suggest to do this one, and then, but this would be like a challenge mostly for students that their projects will be using UNet or similar architectures. Okay, so this is how much I can say, and it's good actually to put a note here. This is May 31st notes. Okay, and these PowerPoints also they will be shared with you. Now, what you're going to see very soon is that you'll see these labels of everyone on the Google Classroom. You'll start to do this one, and for anyone who has a project using UNet, you will see how useful this is. And then finally, there will be a homework for everyone. Using deep learning techniques for COVID-19 image data sets. Okay, so this is something very, very important, and it's something which is very, how can I say, well, it's essential. It has to do with medical images, and these types of image data sets, you are going to find X-ray chest images or lung images. You know, mushkrit janë preken shpejt nga COVID-i. Gjithashtu ka dhe imazhe të tjera që janë brain images, where people that suffer from COVID-19, they see some changes even in the CT tomography of the brain. Okay, so this is something very important, but with the techniques that you can learn, you can improve the quality of life in case you have the ability to detect on time whether someone is affected by COVID-19 or not. We could say the usage of this one, it can be that nowadays we could have large volume of input data, and if you assign medical practitioners to analyze all of them at once, this could be somewhat challenging because it might take a lot of time and also attention. But if you do a good training of the neural networks, then you can do the same task at a much faster time. And what is also tricky is that computers, once they are implemented or prepared in a good way, they can do a perfect, they can operate with a perfect accuracy, including also quantitative analysis. Human perception or an evaluator or an image analysis, also an imagerist, they can do good qualitative work saying a yes or no, but computers are very good at detecting also regions of interest quantitatively. And these regions of interest, it could be the, let's say, the relative surface area of the lungs that could be negatively affected by some disease. Okay, in this case, the disease is written here on the slides. Okay, now this homework, it will be for everyone. So it's like a challenge for all of you to go and find out all the possible data sets that you can acquire. And maybe the best way to deal with this one is even having a common domain where you can enter the links or the addresses of where you can find all the data sets. So we are all aware what there is around, what is around. And we can do it also like a challenge, not a challenge, but you're going to get extra points. So let me do this one because we always need motivation. So extra points for students in the class that enter new information and write their name next to new info. Okay, so I believe this is something because the motivation in grade, it has a strong effect. Extra point for students that have new information. Now, this new information can be linked to COVID-19 data sets, public challenges, which are published. I have published on Google Classroom. You can find a link to a challenge which is put out for everyone. And in case, including the students in the class, in case you decide to create a team, you could do that. It would be great actually. Maybe this would be the best thing that you can do as a product of this class. You can create a team, 3 or 4 students. It's your choice. You can register for the challenge which is published on Google Classroom, and you can try to work with the data set. You could do this one both for the homework of this class and also for the challenge, which there is a financial reward for anyone who provides a competitive answer or an answer that does the quantification of the COVID-19 images at a higher accuracy, let's say so. Okay. So these are some important notes which we had to go over. I want to thank some of you that really did a perfect job in terms of labeling of the images in homework 3. Now let's move to, wait a second, to some final elements we want to go over on chapter 5. Now chapter 5 is this one, where we are dealing with image restoration and reconstruction. We said that we can have an image which is initially fxy, so this would be the image, and then we can apply a degradation function which is h of x and y, which is a degradation function in the, let's say, in the real domain, and then we can add also some noise function, and this noise we denote it as nxy. Now this is in spatial domain. From last time we said that all of these transformations, they can be represented in the Fourier domain or transform domain as shown in the second line. What we are going to see today is that when we switch to chapter 6, we're going to see that next to the Fourier domain, which we have pretty often, we've seen this one, we have also a couple or other domains, such as the cosine transform, the discrete cosine transform, the discrete sine transform, the Hartley transform, and we'll see that specific transformations, they can perform or they can help us more in case we choose one over the other. And this all depends on the type of the problem that we have at hand. Practice can tell us which one of these transforms would be better when comparing with each other. Now, these were some notes we kept during the previous lecture, so it's good actually. These PowerPoints will be shared on Google Classroom. You can even have a note of we can look back at our notes we have kept during the class. Now, you can go over these slides, and in principle, what the general aspect is here is that we can implement linear and nonlinear filters over images that have different types of noises. And sometimes some filters, they do operate, or they have do a better job against some specific types of noises. Now, let's keep this here for a moment, and let's switch. Okay, and probably I should also mention, so these were all about the noise. So these are all these examples that are about. Now we have also some types of image transformations, or which can be used for the reconstruction, where the problem could be to reconstruct a specific object based on a series of projections. Now, this type of reconstruction, it often happens in computed tomography, and which is also called CT scan, computing tomography. And an example, let's see here. So let's assume for a moment that we have an object which is shown here in this slide, and this object. Wait a second. This object can be, let's say, something like a sphere, which is this. On the left side, on the top side, we have an object which in the form of a sphere, and then using CT scanning. And CT scanning is when you have the scanning and we're trying to obtain a three-dimensional picture from having the scanning from different sides. Okay, because what can happen is that an object which is undesired object, it can be inside the human body, and this object can have a shape like this. It could be, wait a second. So this could be the object which we don't like to have it an undesired object. Of course, this is way larger. And then when we do the scanning, we can send a beam of electromagnetic wave radiation, and in this axis. And then what we're going to observe is that we may observe a line. Okay, we may observe a very thin line, and probably this can be very thin to the degree that even the scanning cannot catch this up. Okay, but then what the CT scanning can do is that we may require several scanning from different angles, trying to figure out if we have some object of interest. So if we scan from this side or from this side, you might see almost nothing or very thin line. Okay. Now it depends on the resolution of the wavelength that we are operating with to distinguish whether we can pick up this line as thick as, who knows how thick this is, whether we can pick this one or not. But if we keep rotating the scanning, moving in such a geometry, we might then send the electromagnetic wave in this direction, and now there is a higher probability to pick up this huge area because there is a higher scattering cross-section when we hit it with a wave this way when compared to hitting it with a wave in this direction. Okay, so once we do a scanning around, we have a high probability to catch this up when we are sending a wave, incident wave this way, and this will be absorbed here. There is a smaller probability when we send the wave this way, smaller probability when we send it this way, because the flux, it will be probably almost negligible, because the intersection of the incoming wave with the effective cross-sectional area, it is going to be very small. And what is interesting is that this type of scanning all around that we move, there is also an equivalent principle, which I may talk about this one just at this stage, which has to do with the capabilities of the computational imaging. So let's imagine for a moment that we have a patient, and patients normally, there is a chair, and the individual, let's say, I cannot draw it very good. So here we have the human body, okay. Then and the patient has interest. They have good hair. They have an interest to scan the brain or the chest, and they are inserted inside a huge region where strong magnetic fields can be generated. And these strong magnetic fields, they are changing as a function of time. So these magnetic fields, they are a function of time. In case this is happening, then that means we have induced also some electric field, which is also as a function of time, which is different from zero, because electric field and magnetic field are coupled. This much information, we take it for granted. But what can happen afterwards is that as a patient is inserted inside this system, we are going to have the scanning of a three-dimensional object. So this is a three-dimensional object using computational imaging. So let me write this one, computational imaging. We can get this whole information on two-dimensional layout. Let me call it this way, layout. And this is, of course, this is very beautiful mathematical apparatus. It's really good tools, and there is a huge research area which focuses on computational imaging. But what we are going to see together, probably in the second year, is that these tools, which can project three-dimensional information on a two-dimensional layout, this is something beautiful, which has to do with these tools, such as Fourier transforms. So Fourier transforms is the key ingredient of the whole mathematical apparatus to ensure that this information, which is in 3D, can be projected on this two-dimensional layer. So now this two-dimensional layer, so this would be some object which would be in the human lungs. So all of these projections, imagine for a moment, so let's try to draw the map of the world, okay, which can be imaged on a cylindrical structure, but we can use mathematical apparatus from this two-dimensional image on the cylindrical coordinate systems to construct 3D. And 3D, we can also imagine as if you are going to reconstruct a tree, okay? So this is possible, but this aspect of computational imaging, this is something we can discuss later. What is related to what we see in this slide is that we can have an object of interest, which could be even something like this. If we want to pick up whether there is something or not, we can send a beam from the right side, as shown in figure B. And as the beam is sent from the right side, we can record an absorption profile. So now let's imagine for a moment the object which is shown in white color, this absorbs a lot of the light, okay? Which means that it's not transmitted. But the background, which is in black, imagine for a moment that no electromagnetic wave is absorbed. I know that in this class we have electronics engineering, that they know that there is a coefficient which is gamma, which is a propagation constant, and this is gamma is equal to alpha plus j beta, and this is called a function which is called the attenuation constant, and this is the phase constant. Just for a moment, allow me to see whether, I just want to see whether you see the board or not. You do see that? Okay, that's good. So now these attenuation constants, you can imagine that as the light is passing through an object that has some structure, or that the electromagnetic wave can be absorbed, then with a high intensity, we denote that we have absorbed this much information, which now is going to create a straight line. Now, we observe that there is a, let's say, in this axis, we're going to absorb a high amount of the incoming electromagnetic wave. Then we can also send the light from a different angle, or comparing to this case, we can imagine that we are sending an electromagnetic wave in this direction, and we want to see if we have some object which is going to absorb the light. And then we can have a projection. Then we send the light from this other angle to see if there is something which we can, from where we can observe more information. And if we do the scanning from the top, we're going to see a straight line which is shown at the second row of the images in the center. Now, if we add up together the image which is on the very right side of the first line of images, which is the scanning, which shows a horizontal line, we can add up also the image which is a vertical line, which is showing the absorption spectroscopy whenever the light is sent from the bottom. So if you watch carefully, you can see that there is a electromagnetic wave which is sent from the bottom. Whenever there is a high absorption, we denote it with a white color. When there is no absorption, we put it dark, which means 0. Then, if we add these two together, we get this image, which is at the second line of the images at the very right side. And this is showing that there is kind of an intensity, which looks like a square. In fact, we may be interested to get the high resolution of this image. And in order to do this, we don't use the scanning only at two orthogonal directions, which means we choose one axis and then we select another angle which is 90 degrees with respect to the original wave. So we don't choose only two directions, but we can choose different directions, which if we do the scanning here, we'll have to send the light at different angles. And the higher smaller the angle between two subsequent waves, that means that we are going to have a higher resolution, which means in this slide, we are having the light sent at with an angle difference of 90 degrees, but what would be better is sending the information, the electromagnetic wave, at as small as 1 degree. That means that we'll get a higher resolution. Here we see another example. We see that we have an object of interest shown at the first object, then at the first object from the left side at the first line, and then we can we can see what is the absorption profile if we send the light from the, let's say, from the left side. We see the image shown in the middle at the top line. Then we can send we can measure the absorption by assuming that we are sending a light sent at an angle of 45 degrees. This is what we observe, and then we can have another beam of light which is sent at 90 degrees, 180 plus 45 minus 45. So the image which is shown at the bottom, the image at the middle of the second line, this is constructed. You can see that we have an absorption profile obtained when we have an angle of 0 degree and 90 degree. And then the other two lines, they are created by trying to measure an absorption profile by having 45 degrees and minus 45 degrees. Now, these are the first 5 images. If we want to have a higher resolution into trying to figure out what object we are looking at, we can have several absorption profile measured not with a resolution of 45 degrees each time, but as small as 5.6 degrees. And then what we observe this image, which is at the bottom side on the very right, so on the right side of the second line at this slide. Now, here we have another example, and probably let's write So initially, let's have a look. We have an object where we have here a square and some elliptical shape object. And let's assume that we'll try to reproduce these images by using several projections. So this is the task that we are trying to do, okay? So we can obtain several projections. We have to merge them together, try to see what was the original object. In order to do this, we can try to observe what is the possible measurement in case we do an absorption spectroscopy, sending the light at an angle theta equal to 0. If we send the light through an angle theta equal to 0, that means that the light will be approaching from the left side, and it is expected to draw a white line wherever you can think of this one as if this is the shade. Sigurast here ecdicatroid, and the here ellipsid. So if we think it in this format, so we define what is theta. Let's see here, evaluate selection. So this is what we are observing from these two objects. Okay, so sorry. So we see a shade of this object all this way around, and then the projection of this elliptical shade. Actually, I said to you that this should be theta equal to 0. Apparently, this is theta equal to 90 degrees. So you should be, and let's see what we obtain. It's a theta. So let's remove this theta. Let's define a new value for theta of 45 degrees. And let's see what is the new image. So it looks like, let me think for a moment. So this is 45 degrees. So it looks like this is measuring the 0 with respect to, I'm trying to think about this one, about pi over 2. So to me, this theta equal to 0, it looks like this is respective to the vertical axis. Okay, so we should conclude this one apparently, because that's why that was, and also similarly, of course, all the thetas, they are respective to the vertical axis. Because theta minus 90, anyway, or let's leave it for the moment. We just noticed that when we use the angle of 45 degrees, this is the profile that we see. And actually, it makes sense because if we send the light during this axis, actually, let's just try to do it like this. So this will be a straight line, which is going to point this way, and we can try. Anyway, so this profile is going to be, so once we use an angle of 45 degrees, this is what we are going to obtain. Okay, so, but then if we use an angle of, let's see, the subsequent one, let's use an angle of 120 degrees. But for a moment, an angle of 120 degrees, which apparently should be with respect to the vertical axis, this means that the light will kind of approach from the, let's see what we observe actually. Let's remove this theta. Let's plot this again. Okay, so this is now we are approaching, or we are recording the absorption profile of this object at this other angle. Now, in order to get a higher resolution result, we can now change the angle theta as in smaller steps. So we can make steps of 5, and let's have a look. For example, theta is equal to 120. This is let's remove these variables, and Let's delete this. Yes. Let's have delta theta. Let's have this one equal to 5. And then let's have the theta. Let's change this one from 0 to 175 using steps of 5 degrees. So if you want to see this theta now, this is 1, 2, 3. Oh, okay. This doesn't look what I was. Okay. Sorry. So this theta, it's just going 0, 1, 2, 3, 4, 5, 6, 7, etc. What I was intending, let's do it this way. So let's consider this one theta 2. Let this be theta 2. Let this be d theta. And d theta is equal to 5. Let's implement this one, evaluate selection. So theta 2, we have less angles. And these, we have here steps of 5, 0, 5, 10, 15, 25. So the resolution, the angular resolution is something around 5 degrees. Theta, apparently it has 1 degree. So if we do the scanning by calculating the absorption profile as a function of theta and theta 2, most probably if we use the absorption profile using the thetas, we are going to get a better result because we have a resolution of 1 degree. So we're carefully trying to catch up the curvature which could be around the ellipse, which we have in this case. Theta 2, it has a smaller resolution. Then let's see what we get here. So we have I2 reconstructed all using theta. So I2 is all in there. Let's see, theta 2, figure 44. Okay, it does take some time. It's really okay. So this is the profile that we observe if we do the scanning with a resolution of 1 degree. Okay, if we apply a different resolution, or let's call it warts, with a warts resolution, let's call this one reconstructed, let's call this 5, not all, but steps of 5, and let's make this theta 2, and then figure 45, and then let's put here tick and top. Okay, so TikTok, it took 11 seconds approximately to do this calculation. So normally this is a large, it takes computational time wise, it takes some time. And here we can see that the object that we observe here, it has less noise, where we use the resolution of 1 degree. Here we have used a resolution of 5 degrees, so we can really see some features as if, so we see some lines, and the angle between these lines, most probably you can argue that it's going to be equal to 5 degrees. You can try to do a better job by having here d theta equal to 0.5. But this one is going to take a lot of time, most probably. So if we do it this again, d theta is 0.5. But then once we let this running, we should be doing something else. So theta 2, let's wait a second. No, let's define this one as theta 3. Evaluate selection. Theta 3, it is 351 different values. They are all having step of 0.5 as it was expected. And let's see here, let this be theta 3, image reconstruction having 0.5. Let's call it this way. And this is image reconstruction having steps of 0.5. And we want to plot this one into a different figure. And let's give some more memory to the poor machine, and we evaluate the selection. And once this is running, we can go back to the PowerPoint and see where we left. So this is an important tool which can be used to construct an image from several projections. And with projections, this is what we mean. So we try to produce a lot of shadows of this object, and then afterwards we add up all of these shadows. And if we have a very good resolution in the angular resolution, we can pick up even objects that have a specific curvature, as is shown here in this case of this ellipse. Now, there are some other aspects regarding to chapter 5, but it has all to do with similar principles that we used so far. Now, at this stage, we can not skip, but we can go. So this is figure 46. So this was the last figure. It might be difficult actually to figure out how much difference there could be between figure 45 and 46. But let's see, it took approximately 34 seconds. And actually we can do a comparison between these. So the previous variable, how did we call it? The previous variable, it was called 0.5 rec5, okay? So we can call II, this is equal to we're just calculating the difference between these objects, and let's see figure 71. Show II. Okay, so now what do we have here? Apparently, in this difference between these objects, let's try to understand what we have. We see, actually, these are kind of the negatives of each other, because the dark spots here, they're like the brighter spots on the other side, and this looks like a nice rhombus structure, which is created by all of these lines. But now let's try to remember, why do we get such a distinct problematic resolution in here? So when this was 5, okay, probably this was the resolution which was composed of 5 degrees, okay, and here this was the, no, there's a wrong. Is there something wrong here? No, it's correct. So this is the resolution when the theta, it had steps of 0.5, and this was the resolution when we had the angular resolution equal to 5. So that's why we can see those. Okay. Okay. Then this is all regarding chapter 5. You can. I strongly suggest you to go over the textbook and to learn more. And actually, learning more, it will be equivalent to you understanding more of the theory for both linear and non-linear filters. Essentially, we have mentioned that the linear filters are bad because they smoothen the information, they diminish the high frequency terms at the edges. This is not something that we want, and non-linear filters do exactly the opposite, which means that the non-linear filters, they preserve high frequency terms at the edges, so we preserve the edge. Now, this was most of the important information from chapter 5. Now, let's go to a new chapter, which is going to be chapter 6. In chapter 6, we're going to talk about several important concepts. So we're going to talk about image transforms and also the wavelets. Now, when it comes to image transform, the first thing I can strongly suggest to all of us is, so this FFT, this has to do with Fourier transform. FFT, it stands for fast Fourier transform. Wait a second, so this is called fast Fourier Fourier transform. Fast Fourier transform. So Fourier transform, it was known in the literature for some time, for quite some time. And Fourier transform, it dates back to Fourier, which could be some information or that was among mathematicians like 150 years ago. So it's really some old piece of information. And it is amazing how they thought about this one at such an early time, which for this one, they also needed the huge contribution provided by the Italian mathematicians, where they needed the square root of -1, okay, which is equal to j or I. So you can call j. It's often seen this way. And now let's see for a moment how will this fast Fourier transform represent itself. So let's do here help FFT. Let's see what step-by-step procedure we need to do. So now I just copy pasted this one, and this is what I get. Okay, it's the same thing I see over there. So this is the discrete Fourier transform. This is, let me try to see. This is xn, and this xn, we multiply this one by a kernel. So this one, which we see right here, this is called, so let's make this one in blue. This one in blue color, this is called a kernel. Now, this kernel, it is equal to the exponential of the j times k times x. Now, this x, this corresponds to the real domain. The k, it corresponds to the Fourier domain or to the reciprocal domain. So we have several synonyms. So there are quite a few to remember. And this whole construct here, this is called the kernel. And in order to calculate the fast Fourier transform, what we do is that we have here f of x. This is the function that we have. We multiply this one with the kernel, and then we put the summation sign. I'm not sure if I can do a good job, so let's do this one. If we want to insert a symbol, and this symbol is going to be the summation sign. If I cannot find it in less than 5 seconds, I'll skip it, because I may be. There's going to be a sign which looks like this. So let me insert this one. It's not really this one exactly. It's a mathematical apparatus or mathematical. It's like the sign which we do just before the concept of the integral when we take calculus 1. But I'm not very well versed in PowerPoint or to insert this, because this maybe does not have an equation. Anyway, let's leave it for a moment. Insert an equation is not, it may not be the perfect thing. So this in here, this is like the summation of all of these terms. In more analytical expressions, it would be equal to some integral of the f of x times this kernel times dx. Okay, so this is how we take integrals, right? This is dx. But in textbooks, this is what you're going to see. But what is essential for you is we have to identify that this is the real domain. We multiply with these complex numbers, and then we integrate. If we use the summation, we don't have this integral, this delta x, okay? And if we don't have it, let's have a look how this whole expression looks like. Now, at this stage, we can provide a small example. We can say that a, this is equal to a series of number, which can be 2, 3, -1, okay? So this is a. If we want to calculate the fast Fourier transform of this a, you can So I'm just reading, I'm going to read what is on the, this we are recording. Sometimes I do forget to click the recording, but it looks like the xk, this is capital xk, this is equal to a summation from 1 to n. Okay? This is from 1 to n. In this case, the n is equal to 3 times xn. So this is little xn times exponential minus j times 2 pi. So this is exponential minus j times 2 pi times k minus 1 times 2 pi times k minus 1 times n minus 1 divided by n times n minus 1 divided by n. So this is what we see. Let me see if we have something wrong. And k, it is going to be from 1 to n. Okay, it's 1 to n. That's good. So this is the expression. So this is how we can calculate the Fourier transform. Now the vector we entered here, it was 2, 3, minus 1. So xn, let's write this somewhere here. X, little xn, this is a vector 2, 3, minus 1. Now this chapter 6, it's full of this elegantly put type of transformations, which can transform the data from one domain to the other. And I would strongly suggest you go over these transformations and work them with pen and paper, because you really, it's fun when you do this one on your own. So let's see here. This is the image, not image, sorry. This is a data set in the real domain, which are just these 3 numbers. The Fourier transform of this one is going to be again 3 other numbers, but there is a high probability of them being complex numbers. So let's say when k is equal to 1, we can say that the capital X1, this is equal to the summation from 1 to 3. So this is from 1 to 3 of what? So let's set first n equal to 1. When n is equal to 1 and k is equal to 1, let's see what we observe here. Let's substitute. N equal to 1, x is 2. So this is equal to 2 times the exponential of what? Now, since n is equal to 1, we see that this exponential, it will, actually, let me think for a moment. Yes, this whole exponential, this is going to be minus j divided by n. N is 3. Let's put here 3 times 2 pi times k is 1. 1 minus 1 is 0. So minus 0 times 0 times 0 again. Okay. Now e to the power 0 is equal to 1. Okay. So that is, let's remove also the summation here. Plus, so we are summing over n. Let's not forget that. Or maybe let's preserve it just to remember that we are adding over 1. Then here we have n equal to 2 and k is equal to 1. Okay. And then let's move ahead. When n is equal to 2, we are going to have here x2 is 3 plus 3 times exponential minus 2 pi j divided by 3 times, well, it looks like I need a space, times k minus 1. K is still 1. 1 minus 1, 0. So we multiply here with 0. And 2 minus 1 times 1. Okay. And let's add here again, plus 2, 3 minus 1. I'm going to use this one, 2, 3 minus 1. So it's going to be way better if we do it like this. Plus 2, 3 minus 1. Now this is going to be minus 1 times exponential of minus 2 pi j over 3 times this term. This is when n is equal to 3 and k is still equal to 1. Okay, so this is then k minus 1, this is times 0 times n minus 1 times 2. Okay, so we found the first number. So this is the first number, this is the capital X1. So let's see what we get. exponential to the power of 0 is 1, okay? So this will be equal to 1. This is also exponential to the power of 0. This is also 1, and this is also 1. So finally, we observe that I'm using the board very badly, but this was the small x, and in the Fourier domain, this would be equal to what? We have 2 plus 3 is equal to 5, minus 1, this is equal to 4. So the first element that we get in the Fourier transform, we get this 4. The second element, let's put here, k is equal to 2. I'm not sure how much of the board we are seeing. Wait a second. So when k is equal to 2, we're going to get here x, k equal to 2. This is going to be equal, so we are going to sum over n to 3. This is, we're doing just this as a reminder. And then we go ahead. X, when n is equal to 1, what is x1, the small x? This is 2 times the exponential of minus 2 pi j divided by 3. And small divider again, this is n equal to 1, k equal to 2. So there's 2 pi j, k is equal to 2. 2 minus 1, it's 1 times n minus 1, 1 minus 1, 0 times 0, okay, plus the second element, it is 3 times exponential of minus 2 pi j divided by 3. Sorry, this is the second term. This is n equal to 2, k equal to 2. Then here, 2 minus 1, this is times 1 again. Plus, the other term is when n is equal to 3 and k is equal to 2. So k, let's not forget k is right here, right? So that's why k, it is not changing. This is minus 1 times exponential of minus 2 pi j divided by 3 times k is 2 minus 1, that's times 1 times n minus 1. 3 minus 1, this is 2. That's good. Well, we get a complex number. Of course, we get a complex number because Fourier transform, we go from the real domain to the complex domain. And but let's see what we obtain. So this is e to the power 0, so this is equal to 2. This is 2. 2 times 1 plus 3 e to the power what? This is 113, 2 pi over 3. What is 2 pi over 3? 2 pi over 3, it is pi is 180 divided by 3. This is, pi is 180 divided by 3. This is 60 times 2. This is minus 120 degrees. So this is e to the power minus 120 j. Okay, minus the exponential. This is pi over 3, it's equal to 60. So let's write this one, e to the power minus, so pi over 3, it is 60 times 4. This is minus 240, minus 240 j. So in principle, we're trying to determine the, let's say, the Fourier transform of this data, but having, so we also notice here that the phase space hapsira fazore ne kemi fragmentizuar në 3 pjesë. Pse? Se në fillim kishim këndin 0 grad, në këndin 0 grad është këtu. Pastaj kemi këndin minus 120 grad, minus 120 grad është këtu, pra kjo është 30, pra kemi këndin minus 120 grad, kemi pastaj edhe këndin minus 240 grad. Minus 240 grad, pra i shkon me 128, kjo është 60, dhe 60 vim këtu. Kjo është, në fakt, për arsye simetrie, kjo është 30, kjo është 90, kjo është 90, në fakt, kjo është 90, kjo është 120. Pra, ne çfarë kemi bërë në fakt, esencialisht kemi fragmentizuar hapësirën fazore, që është 360 gradë, në 3 këndet barabarta. Po kemi marrë këndin n fuqi 0, n fuqi minus 20, n fuqi 120. Këtu pastaj mund të bëjmë edhe disa fishtime të tjera. Kjo do jetë barabartë me 2 plus 3 që shumëson. Dim dhe edhe një tjetër, që do ta I'm sorry, Tani, that we should never forget this, but it's an easy rule, which states that e to the power theta it's equal to cosine theta plus I times sine theta. So then e to the power minus 120j, this is going to be equal to, so this is the angle. So now, what is the cosine of this element? The cosine of this negative angle, actually lose here, because the projection in here, this is a negative number, and the sine is also a negative number. So actually, when we are in this quadrant, in the third quadrant, the sine and cosine, they are negative. So let's substitute them here, actually. So what is, if the angle is 120, what are we going to get? This will be sinus I 3 dietas. Sa sinus I 3 dietas është një dyta, so we get here minus 1 over 2, minus 1 over 2, minus I sine square root of 3 over 2. Square root of 3 over 2. Then here we get 3 times minus 1 over 2 minus, let's write here j. I like j square root of 3 over 2. That's good. Then minus, we go again here, minus, what is the, so let me write this here, I find it a little easier. This is going to be equal to minus 240 is this one. This is cosine of this angle, it's minus 1 over 2 again, minus 1 over 2, plus j square root of 3 over 2. So this is minus again, this becomes plus 1 over 2 minus j square root of 3 over 2. If we work out with these numbers, we can then conclude that the second value in this Fourier transform is equal to 2 minus 1.5 plus 0.5 minus 1, 2, this is 1. And again, yes, this is something like 1. So the real part of this number is 1. The complex part is going to be the following. So let's do it like this. This is going to be plus j. Of course, we're not going to do this one for each element, okay? But at least once is that at least we have to confirm whether we did this right. If we don't get this right, we have to fix this one at least once. So j, this is going to be 3 times square root of 3 over 2 with a negative sign, yes, minus square root of 3 over 2, which is then equal to minus square root of 3 over 2 times 3 plus 1, 4. So this is 4. So this is going to be minus 2 square root of 3. Okay, I think we did this. So this is going to be minus 2 square root of 3, which is approximately, this is 1 minus j. Square root of 3 is 1.7. Times 2, it's 3.4. 3.4. Okay, so now with all of these steps, we can try for a moment. So we know A, and let's see what we are going to observe here. So this is A, and let's call this one capital A is equal to FFT, the fast Fourier transform of A. So the numbers we get, the first number, it is 4, which is, that's what we observed. The first number, this was this, so this is 4. The second number, we get 1 minus 3.4 j, okay? So let's check if this is correct. This looks like it is correct. This is 1 minus 3.46 j. And the last number, apparently, it's 1 plus 3.46 j again. So this is how we do this, okay? At least we confirm that this far we did a good job, okay? Now, similarly, we can also calculate when k is equal to 3. We say that in the complex number domain, this x for k equal to 3, it will be equal to the summation of all of these terms. And in fact, we get 1 plus j times 3.4. Now, one thing which is essential is that the summation of all the terms in the Fourier domain, they are all going to be a real number. It is not going to be a complex number, which means that if we calculate it, so the first thing is that the first element is always the sum of the terms. Okay, kjo katra assume 2 plus 3 minus I, okay? That's the summation of these terms. Then the other two terms, they should be complex conjugates of each other. So each time, if we have, let's try it like the following. If we do the summation of all of the terms of the fast Fourier transform of a random number integer generation, sorry, 1 by 10, the summation is going to be, but let me think, why did we get something like this? Let's see, what is random number generator? Well, okay, so this is 1 by 10, this creates, we should not do this one. We wanted to have random number generator 10. No, it should be 10, 1. Okay, so this is, let's consider this one, small b is equal to an answer. So we have a variable. We randomly generated this number, and then we can calculate the fast Fourier transform of b, okay? And then we can sum the answer. When we take the sum of the answer, we are going to get a real number, because always the fast Fourier transform is going to produce complex pairs of complex conjugates. So if we have one complex number, which is 3 plus 4i, definitely there should be another complex number, which is 3 minus 4i. So in this perspective, actually what one could also consider is the following. We could, so if we want to save the data, so let's say, for example, we have the b, okay? So b is this, then b, it can be equal to fast Fourier transform of the table b. Here they are. And let's try to find the complex conjugates. So let's have a look at this number. This number, minus 4 plus 11, 35i. The complex conjugate is at the very bottom, okay, the very last one. Then this other number, its complex conjugate is found right here. Then this complex number, its complex conjugate is found right here, okay? And similarly, the complex conjugate of this number, it's right here. And since this is an even number of cells, because we have 10 of those, we have two real numbers. So this is pure minus 5, okay? And this is equal to 55. Now this 55, it is sum of all of these b's here, okay? So because this is 55, if we do the sum of the vector b, this is 55. This was also what we got when we got the first result, because we were adding all of the accents, assuming that the exponential, it will always give a number equal to 1, because it was exponential to the power 0. Good. So now we did enough work into deriving the Fourier transform of an array of numbers in this way. But now, based on the concept that we can, not concepts, let me say it this way. Based on the little tools you are presenting, I think yeah. So based on the tools which you have learned in linear algebra, I can remind you that, so let me say it this way. We are using MATLAB in this course, okay? That's what we are trying to show. MATLAB, it stands for Matrix Laboratory, which means that all the operations that are done using MATLAB, they are using matrices. And matrices, they are linear operators. And linear operators, they are represented by matrices, which means that fast Fourier transform, this FFT, it is equivalent to having a transformation matrix A, let me call it actually a transformation matrix T, or a Fourier transform. Now, with this double-sided arrow, we just want to represent like this is a matrix. Now, what is the dimension of a matrix which is going to convert a vector which is 2, 3 minus 1, because we know that always A, if this is the matrix A, times x, this is going to be equal to b. So if x is equal to 2, 3 minus 1, this is 2, 3 minus 1. This is in the real domain, okay? What was the complex domain? It was 4, the first element. The second element is 1 minus 3.46, 1 minus j, 3.46. The third element is 1 plus j, 3.46. Now, this is a matrix which is 3 by 1. Yes, 3 rows, 1 column. This is also 3 by 1. The question is this. what could be this matrix here, which should multiply this one into getting this result. Now, this matrix, it should be a matrix which is 3 by 3, okay? And it looks like the first one is going to be 1, 1, 1. And by the way, what we can also interpret is that they are 1, 1, 1 because we notice that the first value is always the summation between these. And the question is, what could be the second row and what could be the third row? Because we know that whenever we do matrix multiplication, this is what to do. The first row multiplies this column, the second row multiplies this column, and this is what we are going to obtain. In fact, we have the result here, what it should be. I'm sorry that I deleted this one, but it looks like at least the second term, this would be exponential of j. So let's do this one. This is 2 pi over 3 j. Okay, this is e to the power minus 120, minus 120 j. The other element is e to the power minus 240j. So I'm writing this in a very small 240j. And the first term, I forget what it was, but it's going to be 1. I think this is 1. Because when n is equal to 1, this is also going to be equal to 1. Now you can figure out yourself what are these two other elements, okay? And you can. Okay, then, so this was Fourier transform. A similar way, we can also calculate present now. Let me try screen. Okay, so this is what so we had a series of numbers, which was as a function of x, we have f of x, and we needed to calculate the Fourier transform. We learned how to do it. Let's move to other elements. So yeah, so this is how the Fourier transform is calculated. This equation which is seen at the top, and we also notice that this matrix that we were trying to write it down, this is how it is going to look like. Okay, so we have the Fourier transform, which will be in units of u. When you say units, we are transforming from the domain represented by x into a domain represented by u, and we see that this vector, which has 8 values, which goes from 0 to 7. All of these numbers will be rotated by an 8 by 8 matrix, and we know that if we multiply an 8 by 8 matrix with an 8 by 1, we get an 8 by 1. So this matrix multiplication, which is seen in this slide, we understand that it is going to be, it is correct, okay? But one thing that we notice is that each row of this matrix, which in fact represents the Fourier transform, it has a higher frequency each time, okay? So, for example, here, we have here e to the power minus 120j. Here we have e exponential to the power minus 240j. So the frequency, it had some 2 pi over 3. Now, let's try to determine actually the third row. What could be the third row? We can calculate this fast. So when when k is equal to 3, this is going to be exponential to the power minus j times 2 pi over 3 times 2 times 1. That's one term. And the other one is exponential to the power minus j times 2 pi over 3 times 2 times 2. Then this we deserve to give these numbers is 1, 1, 1. Sorry, it's going to be 1, 1, e to the power minus 120j, e to the power minus 240j. And these are the terms which should be included here. They are going to be pi over 3, it is equal to 60. Times 4 is 240. That's good. Actually, I should have predicted this one, because this is symmetric. So this is minus 240j. Why did I see this before? And then here we have pi over 3 divided by 3. This is again 60. 60 times 6, we get, what is 60 times 6 is 360. 360 is 2 pi, but this does not make minus 360 j. So now these terms that we see them in this way, these are just oscillatory functions. Okay, so this is one way how we can represent these. And when we say that these are oscillatory functions, we can see that if we go lower and lower along the matrices, we can see higher frequency terms. Okay, at the top, if you see the first row, actually I should be able to write something down here, which this is pen color. Let's make this black. So actually here we observe low frequency terms. Why can't I do this? Okay. So here we have low frequency terms, and here we have high frequency terms. This is as much as information that we need for the moment. Then a similar representation we see also here. So we have other transformations. Now we are specialists how to calculate the discrete Fourier transform, right? The first one is called the DFT, and we know how to obtain all of these numbers. When I say all of these numbers that are hidden in these matrices. This was a 3 by 3 matrix. We can have even larger matrices, and the example shown here, they are 16 by 16. Now, we see here the DFT, which is the discrete Fourier transform, or the Fourier transform. The second one is DCT, which stands for discrete cosine transform. We have also Walsh-Hadamard basis, which is a C, which is WHT, which is like white, but it's not white. It's like Walsh-Hadamard basis. Then we have the slant basis, which is another basis which is unique. We have Haar basis. Haar basis is a very good type of basis which produces very nice wavelets. We have also Daubechius basis. So there is a mathematician, I believe this is like French mathematician, who came up with these wonderful functions, which can have very good applications in the signal and systems, or in signal analysis. And they do a good job. They're called DB4 in this case. There are Daubechius series of type 3, Daubechius series of type 2, 3, 4, etc. So these are, as you can see in this slide, matrix representations of the numbers with which we multiply numbers. When you say numbers, in this case, these are the values which have to be multiplied a vector, which is 16 rows and 1 column. Transformimin Fourier ose transformimin e kosinusit, ndërkohë që kemi 16 vlera të ndryshme. Now, in terms of the transformation, we have also the time frequency plane. Now, in this slide, we see the Heisenberg uncertainty principle, which means that the the area in the time frequency plane, okay, sorry, no, pen color. So this area here, it is always constant, okay, this will never change. Why? Because delta t, this is delta t, times the delta frequency. This is equal to a constant. Now I cannot write very well here, but this in principle means that if we have a function in time domain which is wider, that means that in the frequency domain it is going to be narrower. And a good example here is that let's assume that initially we can have a function in time domain which is a step function. Actually, it's not a step function, but it's a delta function. A delta function is a function which is 1 only at a specific value and 0 everywhere else. And since this one has a width, so delta t here is equal to 0. Sorry, this ended up into being a hat. I did not intend to draw a hat, but I cannot do a better job. So if delta t is very narrow, then in the frequency domain, we are covering the whole frequency, okay? Now the same thing happens, let me see. Actually, this graph and this graph, they're both represented in this graph here. we are shown the exact precision where the function is in time, and this is the representation in the frequency, and so on. Now, here we see that in the frequency domain, we know we have a precisely well-defined frequency. What could be this frequency? This could be 30 Hertz, which means that we can have a function which is oscillating with 30 Hertz. If this is, so let me write this one actually. This is something like 30 Hertz per 30 Hertz. And this one is this is an exponential 2 pi times 30. 2pi her 30 bën 60pi. Për kjo do jetë eksponenciale I 60pi her kohë. Now, this is something which we can detail again later. Now, always, well, here we see the example of how we can localize the time and frequency for 128 Dobitsch's basis function. Now, why is this 128? I don't understand it for the moment, but let's try to pick this up. So at the very bottom plane, sorry, not plane. So let's assume this is the time domain, okay? Look, on the horizontal axis, we have the time axis. On the vertical axis, we have the frequency. Now, let the time, let's assume we have very bad resolution in time. Let's say we are going to measure over 128, but let me see for a moment. Am I sharing am I presenting? You are presenting, okay. So let's imagine for a moment that we are measuring over 128 seconds, okay? Pra koha që po maksim është 128 sekonda. I'd like for you to understand this one in a perfect way. So the time domain, let's say that we are measuring, and we are measuring a signal over 128 seconds. That's good. Now, if we want to have the minimum resolution in time, that means that we just know that something is happening in 128 seconds. That means that we are very bad in time resolution, but we are very good in frequency resolution, because this delta frequency multiplied by this delta time is going to be a constant. But now what we can do, if we watch carefully in this slide, what you can do is that we can divide this time by 2. If we divide the time frequency by 2, we are going to have time slots of, what is the half of 128? The delta time here, it will be 64, okay? If this is the time resolution, it's increased, because now, so it's something like this. Let's say, an airplane landed, zbriti një avion, për shembull, zbriti një avion. Po kur e kemi bërë matin e? Ne matin e kemi bërë për 128 sekonda. Ne tani themi, ore zbriti avioni, po mirë është ta gjejmë pak kur zbriti avioni. A zbritën në 64 sekondat e para apo në 64 sekondat e dyta? Atëherë themi kështu ne. Zvogloje pak, arritë rezolucionin në kohë dhe ul rezolucionin në frekuencë. S'ke çfarë të bësh. You're going to lose some information in frequency. So this delta f, now this is 2 times delta f. Whatever the resolution was here, now is twice. But then here we are better. Sorry. Yeah. Well, let's do it like this. So now this is delta t. Well, let's do it. This is 128. This delta t is equal to 64. Okay. So we have a better resolution in time. So now, if somebody is asking, when did the airplane land, we can say whether it landed in the first 64 seconds or in the second. Then someone else might say, you know, I need a better resolution in time. Don't tell me if it's happening during the day or night. Give me more precise measurements. And you say, okay, if you want a better, let's divide this one by a factor of 2 again, or let's do it here. But that means that this 128, it was divided by 2. We got a resolution of 64 and 64. Now we have resolutions of 32. So this is 32. But at this time, this is equal to 4 times the resolution, whatever the frequency resolution was initially. And then afterwards, what we do, we divide again by a factor of 2. Now let's forget of drawing the frequency domain to scale. if I divide this by a factor of 2, kjo 4 delta f, ku do të bëhet 8 delta f, ose na mbaron drasa, s'ke 8 delta f, e lëm të zëmë së shkjo e vogël. So let's divide this by a factor of 2 again. We divide this a factor of 2, and this a factor of 2 here. Then we go to a higher resolution in time. We divide it by 2, by 2, by 2, by 2. And so we go like this. So it looks like in so 128 this is equal to what? 2, 2, 4, 2, 8, 2, 16, 2, 32, 2, 64, 2, 128. 2 në fuqi 7. 2 në fuqi 7. So if you count here, it looks like there are 7 layers, and let's try to count as good as our eyes allow. 1, 2, 3, 4, 5, 6, 7. Për kemi 7, po ta shikojmë këtë figurën, duket sikur ka 7 ndarje. Në çdo moment kemi pjesëtuar gjithmonë çdo zonë në kohë in the time domain, we've always divided by a factor of 2 continuously, and this is what we do. Now, if we are in the, actually now you can also see comparisons. So if you are at the bottom, you have a good resolution in the frequency. If you go at the higher levels, you see that you have a worse resolution in the frequency. What does it mean, having a worse resolution in frequency? Having a worse resolution in frequency, it means, let's do it like this. Pen color, let's do this red. So having a good resolution in frequency, that means that this is narrow. Here we have a narrow distribution. Here this is wide, okay? So we cannot determine, so this is the error in measuring the frequency, okay? And this width in the frequency, this is something in between this one and this one. So if you are to judge, you can say that the frequency at the bottom, or at least here, okay, the resolution here it's high. Why? The error, it is represented by the width of the frequency distribution. At the top up here, the frequency resolution, it is defined by the width of the function. Now, if the function in frequency is wider, that means that the error is higher, or the resolution is worse, okay? So you can see that higher you go, you see a change in the width. But if you see a change, an increase in the width of the frequency domain, we see narrower, the time domain, to get narrower and narrower. With narrower and narrower, we mean noticing that here we have some width, and here the width is really small, okay? Here it's somewhere in between. So this is what we mean with the frequency time resolution. But I believe the idea is clear, and we move ahead. This is the discrete cosine transform. Now, the same way that we have the Fourier transform, which was represented by a 8x8 matrix, we can also think a similar way also for the discrete cosine transform. If you have a look at the book, you can see all of these beautiful functions, which are very elegant and nice, which are going, in principle, are somehow, they are just a simplification of the Fourier transform. And it's not difficult. Now, let's see, this is discrete Fourier transform. And the discrete Fourier transform, let's see what the numbers look like. We have 1, 1, 1, 1. Actually, when we draw this one for a vector of 3 values, we notice that the first row and the first column, they are all ones. Then the other elements, they are represented by these other numbers, which, let me think for a moment. E to the power, so what is this e to the power minus 360j? This is actually, this is also 1. Because the cosine, yes, this is also 1. But now here we have a different symmetry. But these numbers that we can see here, we can easily deduce. And the transformation matrix A of the discrete Fourier transform for n equal to 8. So those frequencies, or let me think. So those W's that you see, ato W janë në fakt, janë n fuqi minus j, që shumëzon 2 pi të tetat. 2 pi të tetat është pi të katërtat. Pra në esencë, po ta mendojmë për një moment, 360 gradë. Po ta ndajmë në 8 pjesë, kemi pi të katërtat. Po ta mendojmë 360 pjesim për 2, pjesim për 2, bëjnë 180, pjesin për 2 bën 4, bëjnë 90, pjesin për 2 bën 8, bën 45. Po. Pra ne këtu po shikojmë pak me kujdes, kemi rritje të frekuencave që shtohen me nga 45 gradë. Pse? Sepse W-ja, which is somewhat, sorry, anyway. So this is representations of cosine and sine of 45 degrees, or 1 minus j divided by square root of 2, and so on. Yeah. And if we have this function, which is 1, 1, 0, 0, 0, 0, 0, this is a vector in the time domain, we can obtain the representative calculation in the Fourier domain by multiplying by this matrix A. Now again, this is discrete Hartley transform. The numbers are going to look slightly different, but here we don't have complex numbers. It's slightly different. Again, we can derive this expression. It's not difficult at all. And this is the what we see here, reconstruction of discrete function by addition of progressive high frequency components. This is discrete Hartley transform. And let's see how many of these we have here. We have low frequency term at the top. So at the very top, we have a constant value, which is very low frequency. And then at the bottom, we have higher frequencies. This is how it always goes. Now, this is the transformation matrix for the discrete cosine transform. Now, the discrete cosine transform, it has to do with the cosines of the Fourier transform. So if we go back a few slides, which was somewhere here, wait a second here. So this is DFT, discrete Fourier transform. All of these values here, we have the exponential, and then if we calculate the cosines of those, we get this matrix, okay? So compare these values with whatever values we had 3 or 4 slides before. And one thing which is wonderful regarding the discrete cosine transform is that it has a higher resolution than the fast Fourier transform, okay? And but it does this one by needing to extend the function from having n data points to having 2 n data points. So if we have 3 values that we calculated the fast Fourier transform before a while, we will have to generate a new vector which has 6 data points and then calculate the discrete cosine transform. Here we have one example. We have the values of 1, 0, 1, 4, and 9. And let me think for a moment. This is the periodicity implicit. Let me discrete sine transform. So these numbers that we saw here, I would strongly suggest you from the textbook, there is an example which is example 6.10. In that example of 6.10, we have 3 data points, 0, 1, 2, 3. 0, 1, 2, 3. If you take the square of this one, y baraz me x në katror, ne gjen 0, 1, 4, 9. Sepse 2 katror është 4, 3 katror bëjnë 9. Pra, mendoni funksionin y baraz me x katror, dhe kjo është vlerësuar te numrat e plot. 0, 1, 2, 3. Dhe pastaj, kur bëjmë 0, 1, 2, 3, ja ku janë ato vlerat. Tek treshi, kjo është diku te 9. Pra, po ta shikoni pak me kujdes pjesën e funksionit nga 0 deri tek treshi, ajo është ajo që sapo thash unë. Dhe këtu për shembull ne shikojmë discrete sine transform which can be done manually as shown in the textbook, and it might be a very good exercise if you do this by hand following the explanation in exercise 6.10. That's good. We started this chapter only with discussing these transforms very plainly. I mean, when you say very plainly, just having to even introducing the fundamental matrix transformation as shown in here. But we know that all of these, we have well-written functions in the libraries of different programming languages. We don't need to do this one each time by hand or with pen and paper. But it's good to understand the basics at least once in this form. Now, the transformations we saw so far, they are transformations in sine and cosine, but then we have some other transformations which are called the wavelet transform. Wavelet, it means small wave. Okay, so we can have wave, but wavelets which are smaller and smaller. And the essence of these wavelets is it's something like this. In Fourier transform, we can represent any function as the summation of a frequency of 5 hertz, a frequency of 10 hertz, a frequency of 15 hertz, a frequency of 20 hertz, a frequency of 25, 30, 35, 40, 45, 50, 55, 60, 65. So we can have multiples of the fundamental frequency. If the fundamental frequency is 5 hertz, then that means that multiples of this frequency, so those harmonics, they can serve to make up any kind of function. Okay, so any kind of function, a straight line, you can represent this one by having some number, you can approximate it by having some number of sinusoidal or cosinusoidal functions or harmonic functions, but with frequencies that vary like this: omega 0, 1 times omega 0, 2 times omega 0, 3 times omega 0. And these, the omega 0 is called the fundamental frequency. The multiples, they are called multiples of the fundamental frequency. Now, the same idea that we use multiples of the frequencies, which can be expressed as sines and cosines, it's also used for the wavelets. Wavelets, they are just some functions of which we can represent them analytically, and then we can modify them. Okay, so examples of these wavelets, they are shown here in this slide. And the wavelets, what we can do with those is that we can change the frequency of those, and we can also change the amplitude. For example, let's compare this wavelet which is initially. So what does this wavelet look like? Let's have a look at this slide. Let's do this in red. So what is this? This looks like a sine. Ducă si sinus. Sepse 0 tek 0, ja? Rritet, bëhet 0 prap, duke si sinus. Nuk është si kosinus, jo, no, sorry. Kjo mund të jetë kosinus, fakt. Sepse është 1 tek 0, ja. Pra, atëherë, po nuk e di ç'është kjo. Maybe, but this looks like a sine. Më mirë duket si sinus, sepse periodën e plot e mbyll këtu kjo. So let's call this a sine, okay? Sorry. Let's call this a sine anyway. And we notice that this wavelet, which is seen here, it can be translated. So this is a translation. Y, this is evaluated, this function at x. This is a function of x minus 2. This is translation of this wavelet. At the same time, what can be done with this wavelet is that we can change the width. So if you see here, we are making it thinner. So the width here, it is 1. Here, the width is made half, is 0.5. But once this is made 0.5, we have decreased in time and we have changed the amplitude. So this is how we can change these, okay? So we have a wavelet, we can translate it as this graph shown here. We can also change the resolution in time and increase the amplitude. So essentially, this is some equivalent principle. The same way we used to have the delta frequency times delta time, it was a constant. Again, final word, decrease the time axis, which is shown here in x, and then we change the representation in the y. Now, these are wavelets, and this is somehow trying to modify sines and cosines. Now, we can stop here for today, and before we stop, do we have any question? A ka ndonjë të paqartë? If not, we can give a short break.